Emerging technologies like virtual and augmented reality, XR for short, are becoming increasingly accessible to schools, thus facilitating a more interactive learning environment. As is demonstrated by a number of studies, engaging students in active classroom activities improves learning outcomes. Yet, there are also challenges to overcome. To get the most out of active learning, the teacher needs to constantly manage student attention, thereby maintaining a common focus on the classroom activity. New technologies like XR change how student attention is distributed throughout a lesson. Consequently, the way teachers manage attention needs to adapt as well. We investigate how the use of XR mechanics, developed for high school level physics and biology classes in Russian schools, impacts the dynamics of classroom attention management. Specifically, we study the way in which XR and the more commonplace interactive whiteboards are combined during concrete classroom activities, and how to resolve possible tensions between technologies and learning outcomes. Since the 80s, education research has experienced a situational turn, the transition from studying the educational process through the assessment of formal curricula to the study of the context of educational activity. Actual real-world learning situations involve more than just written instructions. They unfold over time, in classrooms, with bodies and objects in motion. To be able to study the classroom in detail, we have thus opted for a qualitative video analytic framework set in the tradition of conversation analysis, or CA. It allows us to analyze the details of interaction and to provide a microscopic account of the way new technologies are employed in concrete situations. Our data features interactive whiteboard and XR-based teaching mechanics for high school level physics and biology. In the AR modules, students are able to rotate and highlight specific elements of a digital model and engage in tasks involving this material. The VR lessons provide students with the opportunity to interact with digital props directly. As our research focus, we were particularly interested in two cases. First, when an interactive whiteboard and AR-capable device were used simultaneously, and where the teacher could use the interactive whiteboard to change module parameters. Secondly, where students used VR headsets and solved three-dimensional tasks individually. To analyze the implementation of the educational aids, multi-perspective video recordings, including 360 video, of 12 classes in 4 Russian secondary schools were collected in late 2020. The approximately 9 hours of footage were subsequently analyzed and transcribed using multimodal videographic methods. For the purposes of this work, we highlight a selection of observations from a subset of the data. In analyzing the interaction, our team focused on the multimodal nature of communication, i.e. the role of gaze direction, body position, spatial orientation, and device use with respect to the procedural organization of the classroom activity. We will now highlight two pervasive phenomena visible in the data: gaze desynchronization and the non-mutuality of perspectives. Classroom activity typically involves focused interaction, in which participants coordinate their actions whilst displaying an orientation towards a common point of focus. The introduction of XR technologies changed the way the participants relate to other people and devices during classroom activities. This is because an interface is a potential focal point of attention. When there are multiple interfaces present, attention is distributed among them. This becomes problematic in focused interactions. When whiteboard-focused interactions switched to the AR module, tensions arose between the individualistic focus on phones and the initial focus on the common whiteboard activity. As can be seen in the example below, the teacher attempted to highlight an element on the whiteboard while students were engaged in individual AR activity. Only 3 out of 11 students looked at the interactive whiteboard, and only 1 student chose to subsequently switch their primary attention from the phone to the whiteboard. Thus, the teacher's demonstration was overlooked almost entirely. A prevailing feature of all our classroom recordings was gaze desynchronization. While the students paid attention to their AR devices, the teacher's comments remained unnoticed, inhibiting their overall ability to manage attention. Teachers were thus forced to either reinforce their attention management strategies or to accept the inconsequentiality of their instructions. In other words, all participants in the interaction had to expend more effort to manage attention when AR was used along with the interactive whiteboard. An indirect consequence of the gaze desynchronization was an increased need for sanctioning the behavior of students, as well as a rise in the general strictness of instruction. Let us now consider the second case of interaction using VR headsets. A classroom is a common space. Therefore, all participants are guided by the fact that their actions are mutually visible. Yet, visibility and audibility are not identical for everyone. This makes it possible for students to engage in off-topic chatter in the back rows, for example. Nevertheless, even in this case, participants orient to the fact that they are in a space of mutual monitoring. XR use is characterized by the inability to assume the physical point of view of another participant. This is very different from interaction in a physical classroom and disrupts the mutual visibility that is at the foundation of educational activity. A single learning situation is thus fractured since it includes individual perspectives that are impenetrable to others. In the case of VR, the teacher does not have access to the individual perspectives of students and, firstly, loses control over their progress, and secondly, becomes unable to maintain a common focus. An unexpected remedy for this turned out to be sound coming from the VR speakers, since they produce different sounds depending on student activity, making them available for comment by students and teachers alike. The disruption of mutual visibility excludes the teacher from the lesson and makes it difficult for participants to track each other's progress. To mitigate this problem, it is necessary to provide teachers with the requisite tools for classroom management. This can be accomplished by introducing a screen-based dashboard for monitoring student progress and controlling the content being displayed. Despite the fact that the tasks within VR were planned as individual activities, the students solved them cooperatively. They asked for help and helped themselves, and used physical gestures to help others locate VR objects by temporarily removing their VR helmets. Thus, technology-related tensions were addressed through student initiative. Since the originally single-player interaction in VR turned out to be cooperative, it would be beneficial to support this interactivity on the interface level. One possibility is the addition of gamified cooperative elements, where some in-VR tasks have to be solved with the help of physically present students.